This is the third section of chapter 6 on linear programming, and this is about locating the optimal point. Now, the optimal point is going to be the point on our graphed inequalities that either give us the maximum profit or the minimum cost. So in a previous section, we would have drawn graphs like this with the shaded inequalities, and we'd have had something like this where maybe this area here in the middle represents our feasible region. Okay, and we'll just label that as R. And what we'll find is that our maximizing or minimizing solutions are found at one of the vertices of the feasible region polygon R. So here you can see we've got a polygon like this, and we'll find our solutions to our maximizing or minimizing problems at one of these vertices. Now, there are two ways that we can work out which one of these vertices gives us the maximum or minimum solution. One is called the ruler line method, and the other is called the vertex testing method. So let's start with the ruler line method. So let's say we had an objective function like this that we wanted to maybe maximize or minimize this. Well, the first thing that we do is we're going to replace p with any non-zero positive number. Let's say 10, 20, 30. So you'd have like 10 here or 20 here. That will give you some values for x and y. And those values for x and y will give us, or different values, numbers here, will give us different parallel lines. Now what we do is we put our ruler against one of those parallel lines and we move it perpendicular to it, so it's moving in the direction like this. Okay, and what we'll find is that the vertex that the ruler gets to will be a minimum solution, and the last vertex that a ruler gets to will be the maximum solution. So we'll just put first vertex will give us the solution if we want to minimize something, and the last vertex will give us the solution when we want to maximize something, and that will normally be like profit. So this will normally be like P equals something, and this will be like C equals something. So that's the ruler line method. Now with the vertex testing method, what we do is we solve these the equations of these lines simultaneously and work out the coordinates of each one of these vertices, substitute those coordinates into the objective function and see which one gives us the maximum or minimum answer. So I've just written down what I've said here. So we solve the intersection of the lines simultaneously to find the coordinates of all of these vertices here, and we could use our calculator to help us solve these simultaneously if they're not easy to do. And then we're going to substitute all of these solutions, each one at a time, into the objective function and see which one gives us either the largest answer if we're maximizing or the smallest answer if we're minimizing. This is example 5. Nigel is making ice cream for sale at a charity fair. He makes 2 flavors of ice cream, vanilla and chocolate. Let the number of litres of vanilla ice cream made be X and number of litres of chocolate ice cream made be Y. Nigel decides to use linear programming to determine the number of litres of each type of ice cream he should make. The constraints and the feasibility region are illustrated in the diagram. So it's already been drawn for us. And what we need to do is determine the optimal solution for this problem, given that the objective is to maximize the profit on sales P equals 2x plus y. So in part A, it's about maximizing P equals 2x plus y. Now we're going to use the ruler line method, which means substituting some values in for P so that I can see where the ruler needs to go. So for example, if I made P equal to 10, for example, that one would mean I'd have 10 equals 2x plus y. Okay, 10 equals 2x plus y. That gives me a value for x and a value for y. So from this I would have x needs to equal 5, that will be when y equals 0, and when x equals 0, y would be 10. So I'm just going to plot that line on. So it's there on the graph. I'm just going to pick a different value just so you can see the idea. So let's say I made p equal to 16. So that would mean 16 equals 2x plus y. So if I made y equal to 0, that would mean x would be equal to 8. And if I made x equal to 0, that would be y equals to 16. So I'm just going to plot that on. Okay, so that line's on there. Now, can you see those two lines are parallel? Whatever value I pick for p, I will end up with parallel lines. Now, the idea is that I put my ruler and line it up with one of these lines, and then I move it in this direction, like this. Okay, so I'll just draw that on. So my ruler would be moving here. So often it's helpful to do this question with maybe a set square and a ruler. You get some rulers that got like little rollers on them that help do these questions, but we want to move it in that direction. Now, if we use this method, what I would find is that this would be the first vertex that I get to. Okay, so imagine the ruler's sort of parallel to this, I'm moving this way, and then this would be the last vertex that I get to. Now, since I am maximizing the profit, I want the last vertex that I'll get to, which will be this here. Okay, so last vertex using this ruler line method would be this one here, and I can see the coordinates quite easily. X equals 13, and because it crosses with the line y equals x, that means that y equals 13 as well. So very easy to work out. So that tells me that he should make 13 litres of vanilla ice cream and 13 litres of chocolate ice cream, because x is 13. So 13 litres of vanilla and 13 litres of chocolate. Now I also need to state what the profit's going to be, and I just put 13 and 13, replace x and y with these values that I've got at this vertex here. Okay, so the profit, maximise this profit, it's going to be 2 times by 13 plus 13. So that will give him a profit, the maximum profit he can make of £39. Moving on to part B, this is about minimising the cost, and the cost is given by 5x plus 2y. So what we need to do is to do something similar to what we did before and get some points that we can plot on here so we know what direction our ruler needs to go in. Okay, so let's pick some nice, easy, sensible values for c. So let's say we made c equal to 10, for example. And you know, it's helpful to put multiples of these numbers, then you'll get whole numbers to plot. So that would be 10 equals 5x plus 2y. If I make x equal to 0, that will give me y equal to 5. And then if I make y equal to 0, that will give me x equal to 2. So I can plot those coordinates. 0 or 0, 5 and 2, 0. Okay, so that gives me this line here, so I can see what direction it needs to move in. I'm just going to do one more. One is normally enough, because then you can just get your ruler and line it up to this and move it perpendicular to that. But I'll just pick one more just to make sure I haven't made any mistakes. Let's say I make c equal to 30, for example, multiple of 2 and 5. So that'd be 30 equals 5x plus 2y. So if I make x equal to 0, that means that y is equal to 15. And if I make y equal to 0, that will make x equal to 6. So I'll plot those points. So I've got 6, 0, and I've got 0, 15. and I'll draw my line there. So I'm just doing 2 just in case. Right, so I can see that I will be moving my ruler in this direction, perpendicular to that line. So imagine that line or that ruler moving in this direction like this. What's the first vertex it's going to hit? It's going to be this one. That'll be the first. So that will give me my minimizing. If it was maximizing, I'd look to the last vertex that I hit, and it would be the same one. Over here is like the last question, that would be the last one. But we're interested in the first vertex. So what we need to do is to work out what the value of x and y is here by solving. So we'll just put down first vertex. Yep, we'll find that point by solving x equals y and 3x plus 5y equals 60. We'll solve those simultaneously. Now we can solve this on our calculator. If I rewrite this as x minus y equals 0, then it's easy to solve on the calculator. We'll get a solution of x equals 15 over 2 or 7.5, or y equals 15 over 2. So that tells us how much ice cream he needs to make. So 7.5, 7.5 litres of vanilla, and also 7.5 litres of chocolate if he wants to minimize his cost. And the actual cost is going to be 5 times 7.5 plus 2 times 7.5. That will give us a cost of 105 over 2, which is, that works out to be £52.50. So we'll just highlight those answers before we go on. So notice that the solution is made up of 2 parts: the amount of each of the items that we need, and the profit or cost, the maximum profit or cost. So make sure that you write down both of those things, the number of each item and your maximum profit or your minimum cost. So I've got example 6 here, and it says, using the feasible region determined by these inequalities, find the optimal point and the optimal value when the objective is 2. And we've got 2 different objective functions here which we both need to maximize. So our first job is going to be plotting these inequalities on this grid here. So here's my labeled axis. I think these numbers I've got on here should be big enough to cope with the inequalities I've got here. So the first thing is going to be to write each of the inequalities as an equation so that I can plot those lines, and then get some lines which I can then shade the correct side, and I'll do that by picking a suitable test point. So all of these, first of all, I'll make equal to, and then the third inequality is that 2y less than or equal to x, so I'll write that as 2y equals x. These ones we don't need to worry about because we know where we're going to shade those. Right, so let's start with the first one, the line x equals 2. So here's the line here drawn, and I want x is greater than 2, which is this side. This is the side that I want. So I'm going to shade off the side that I don't want. So I'll just do some shading like this to show, right, this is the unwanted side here. Okay, then we'll move on to the second one here. So we want to draw this line, the line 4x plus 3y equals 12. So what we'll do, we'll use the x equals 0, y equals 0 method. So we'll make x equal to 0. That will give us y equal to 4. And then we'll make y equal to 0. And that will mean that x equals 3. So I now have 2 coordinates I can plot, 0, 4, and 3, 0. Okay, so that's those 2 points plotted and that line drawn. So what I need to do now is decide which side of this line to shade. So I'm going to pick a test point. I will pick 0, 0 to see whether this is the side I want to shade or this side. So I'll just put here test point. You can just put TP. So I'm going to pick 0, 0. So if I put 0 and 0 into this, I will get 4 times 0 plus 3 times 0 is less than 2. So 0 less than 2, not 2, sorry, 12. Now, is that true or false? This statement here, 0 is less than 12, so that's true, which means this test point I picked is on the true side. This is the side that I want. So I'm going to shade the unwanted side like I've done before, and I will shade this side here. So just shade the unwanted side like that. Okay, so we'll move on to the next one, which is going to be 2y equals x. Now to plot this, probably the easiest way is just to pick a couple of coordinates. So let's say if I make x equal to 0, y is 0, I only need one other point. So let's say I make x equal to 2. That means y is going to equal 1. Okay, so that will do. So I'll plot those 2 points, 0, 0 and 2, 1, and I'll draw that line in. Right, so that line is now drawn in, so we'll just label that. So that's the line 2y equals x. And just like before, we need to decide which side to shade. I'm guessing it's the top part. That would make sense, otherwise I've got that little tiny area there. But let's just check, let's pick a test point. So I will pick the test point. Let's go for the point 1, 1. Right, so if I put 1, 1 into here, let's see what we get. We'll get 2 times 1 is less than or equal to 1. Is that statement true or false? It's false. 2 is not less than 1. So that's a false statement, which means the point that I picked, 1, 1, is on the false side. And we want to shade the false side because this side over here will be the true side. So we'll shade the false side. So we'll just go for this shading here, like this. And then the last thing we need to go for and plot are these non-negativity inequalities. So we'll do that. Shade off where y is negative and shade off where x is negative. Now what I can see now is that leaves this sort of polygon here as my feasible region. Now I'll just draw that a bit bigger because it is a bit small. I've got a polygon that's sort of this type of shape. It's something like that. So we'll label that R, and then we can now tackle part A, which is to maximize this P equals 2x plus y. Okay, so I need to know what the slope of this line is, so I need to pick some values for P. So if I say let P equal to 4, for example, that will give me 4 equals 2x plus y. So that will give me, for x and y, one solution would be x equals 1, y equals 2. So my objective line is going to pass through those points. And we'll pick another pair of values, for example. So we could have x equal to 2, y equal to 0. So that's another solution to that. So we'll plot those 2 points and plot our objective line. So there's my objective line in purple there. This is easier to do with a ruler, but I'm just going to show you the sort of direction it's going to be moving in. So it's going to be moving in this type of direction, like this. And because we want to maximize, we want to find what the last vertex this will pass through. Now it is easier to see with a ruler, but as this line moves across here and we draw parallel lines to it, this parallel line, any line parallel to this, the last vertex it passes through is going to be this one here. That will maximize, so that will be 3, 0. So we'll just put down last vertex is 3, 0. So this means that x is 3, y is 0, And if we want to find that maximum profit, it will be 2 times 3 plus 0. So it's going to be 6. That gives us P equals 6. Okay, so that's for the first one, part A. So now we'll move on to part B. In part B, we have a different line. So we'll get rid of this one and these arrows here, and we'll look at plotting this objective line here. So this one is to maximize P equals x plus 2y. So we'll choose a value for P. We'll do what we did before. We'll say let P equal 4. So if P equals 4, we'll have 4 equals x plus 2y. So we want a couple of coordinates from that. So we could have, for example, x as 4 and then y as 0. Or we can have x as 0 and y as 2. So we plot those 2 points. Okay, so there's our objective line drawn in here. Very close to the end of the vertex, but you can see the last vertex is going to be this one at the top, and that's the intersection of these two lines here, the 2y equals x and the 4x plus 3y equals 12. So we'll just put here that the last vertex is the intersection of the 2y equals x and 4x plus 3y equals 12 lines. Okay, so I've used my calculator to solve these simultaneously. Oops. And then what I get is x equals to 24 over 11, and press equals again. I get y equals to 12 over 11. Now if I put those two values into the objective function, so that will be P equals x, 24 over 11, plus 2 times y, that's 2 times by 12 over 11. That gives me 48 over 11. So we'll probably want to change these to mixed numbers. So our optimal point is the coordinate. Now we had 24, 11, so that's 2 and 2/11, and the y coordinate is going to be 1 and 1/11, and then the maximized value, the max value of P, is going to be 48 over 11, so that's going to be 4 and 4/11. So we'll just highlight those answers there for part B before moving on to the next example. Example 7. In a linear programming problem, the constraints are given by this, and we have two different objective functions here which we need to minimize, minimizing the cost. So the first thing we need to do is we're going to plot these lines and shade the correct regions. So the first step is to write each one of these as an equation and then draw a suitable grid. Okay, so there we go, there's our equations. Now before we draw the grid, it might be worth working out some coordinates first, so I don't draw something too small or too big. So for example, on this first one here, I'll just make x equal to 0, which means that y is 90, and then I'll make y equal to 0, which means that x is 30. So I know what size numbers to use there. For this one here, I will make x equal to 0, which means that y is 20, and then I'll make y equal to 0, which means that x is going to be 70. So it looks like I'm probably going to have to go up to about 100 on both, and this one here I would have 0, 50 and 50, 0. So these are the 3 lines drawn and labelled. The next thing I'm going to do now is to choose some test points so I can see which side of these lines to shade. So I've completed the shading, and what you can actually see is that it leaves this whole area here as the feasible region. So all of this, it's like this open-ended polygon, whereas ones before they were closed off, weren't they? So all of this is the feasible region, but we still carry out the same process of drawing the objective line and seeing which vertex we get to first. So we'll start with part A, which is to to minimize this. So when we see minimize, it's about the first vertex. So we want to choose a value for C. So let's make C equal to 60. It needs to be a number big enough that I can draw sensibly on here. So let's say, for example, if I made C equal to 6, it's going to be a tiny little line. So look at the size of the numbers, look for a multiple of these two. That makes sense because then I'm going to get 20 and 30, and they're sort of like large enough to sort of draw a sensible looking line. So if C is equal to 60, so I'll have 60 equal 3x plus 2y. So I can get these coordinates from it as 0 for x and 30 for y, and I can also get 0 for y, which will give me 20 for x. So now we'll plot that objective line. So my objective line is drawn on here in purple. So using our ruler, we would see where this goes as it goes across this way, keeping it sort of perpendicular, the direction perpendicular to this line here. I'm looking for the first vertex, and I can see that it's going to be this one here. So the first vertex that we get to, it will be the intersection of those two lines there. So this line and this line, so that's the intersection of the 3x plus y equals 90 and the x plus y equals 50, which we're going to solve simultaneously. Intersection of 3x plus y equals 90 and x plus y equals 50. So let's use our calculator to solve those simultaneously. So from the calculator we get, let's press equals again, x equals 20 and y equals to 30. Okay, so my optimal point is 20, 30, and then if we minimize C, that's going to be 3 times 20 plus 2 times 30, so that will give us C equal to 120. Okay, so what we're going to do now is get rid of the objective line and plot a new one for part B, because in part B we have this here. Okay, so on this one here I'm going to let C equal 210 because I know that's going to give me like 30 and 70, and I can plot those nicely on that scale. So I'll say let C equal 210. So I'll give us 210 equals 3x plus 7y. So if I make x equal to 0, y will be 30. And then if I make y equal to 0, x will be 70. So I'm going to plot those points and draw the objective line. So there's my objective line here in purple. Now it's already gone into the region R. So if I was to move it back a bit and then move it forward into R, I can see that this is going to be the first vertex that I cross. So the intersection of the line 2x plus y equals 140 and the line x plus y equals 50. Okay, so I've just written that statement down. I've just realised that I'd labelled this incorrectly. I'd put 2x plus y, should be 2x plus 7y. I used my calculator to solve simultaneously, and doing that I get x equals 42 and y equals 8. So my optimal point is just going to be that coordinate 42, 8, and then my minimized cost is going to be 3 times x, 3 times 42, plus 7 times y, 7 times 8, so that will give us 182. Okay, so just highlight those, our minimized cost and our optimal point, then move on to the next example. Example 8, using the same feasible region as in example 7, find an optimal solution given that the objective is to minimize c equals x plus y. Well, this is the same feasible region as example 7, so we don't need to draw it out again. First thing we just need to do is to draw our optimal line, and our optimal line, let's say c equal, let's say 30, for example. So that will mean that 30 equals x plus y. So it's nice and easy. So I'm going to get the coordinates 30, 0 and 0, 30. So I'll plot those two coordinates. So 0, 30 and 30, 0, and draw my optimal line. So just corrected that labeling there. And what I can see is the objective line is actually parallel to this line here. So as I move it across, as I move it in this direction, like this, it's actually going to hit two vertices at the same time. So we'll just write that down, that our optimal line, the optimal line is parallel to the line x plus y equals 50. So we will get to or hit two vertices at the same time. Now when that happens, what we need to do is we need to work out the coordinates of both and see which one maximizes the problem. So let's label these vertices. So we'll call this one A and this one B, and we'll work out the coordinates of both and test them both. So let's start with vertex A. So vertex A is the intersection of the lines 3x plus 90, or 3x plus y equals 90, and x plus y equals 50. We'll solve those simultaneously to find that coordinate. So that gives us x equals 20, y equals 30. So that's the point 20, 30. I'm not going to write optimal point because we don't know if it's the optimal point or not. Let's work out the value of c. C is x plus y, 20 plus 30. So this gives us a minimized cost of 50. Okay, we're now going to compare that with vertex B. So vertex B is the intersection of the lines x plus y equals 50 and 2x plus 7y equals 140. So this was a point that we did work out in the previous example, but if we were to work it out, we would get x equals 42 and y equals 8. So we'll work out the cost. So 42 plus 8 minimized cost, we get a minimized cost of 50. So you can see that this gives us the same minimal cost. And in fact, if we were to pick any point on this line here, we would get a minimal cost, because whenever we put either of these points in here, we would get an answer of 50, because it's the line x plus y equals 50. So this part of the line fits all the constraints. So if we're just going to minimize it, we could just say a value of c equals 50 is going to be our minimal cost. Example 9. So here we're going to use the vertex testing method to solve the following linear programming problem. So it means drawing all of these, finding all the vertices, working out the coordinate of all of the vertices in our feasible region, and then substituting each one in to actually work out which one gives us the minimal cost or the minimum value for x plus 3y. So we're going to start by writing these down as equations. So I've written these as equations here now. I've drawn some axes. The only one that I need to work out coordinates for is this one here. So x equal to 0, which means that y equals 12, and then y equal to 0, which means that x equals 20. So that gives me an idea of how big I need to make my scale, and I need to fit the number 13 as well on my x-axis. Okay, so I've decided to go up in 4s on my axis here, so I'm now ready to draw these lines. So these are all the lines that have been drawn and labelled. The next thing now is to shade the appropriate sides of these lines, leaving my feasible region. So the shading is almost complete. Just need to show my non-negativity ones here, and then I can then look at my feasible region, which it looks like it's that bit in the center there. So we'll just shade this bit here. So this is where we're going to find our maximum or minimum solutions at the vertices of this polygon here. So using the vertex method, we don't draw the optimal line. What we do, we're going to work out the vertices of each the coordinates of each vertex, and then what we'll do is we'll plug those into the objective function. So let's label these A, B, C, and D, so I can see 4 vertices there. So starting with vertex A, it's the intersection of the lines x equals 13 and y equals x, which means the x and y coordinates solving simultaneously are 13 and 13. Putting that into the objective function, we'll get a value of 52. So vertex B, it's the intersections of the lines 3x plus 5y equals 60 and y equals x. Solving simultaneously, we'll get the coordinates 15 over 2, 15 over 2. Putting that into the objective function, it gives us a value of 30. So that's lower than 52, but we need to test all the vertices. Vertex C is the intersection of the lines 3x plus 5y equals 60 and y equals 5. That gives us this coordinate here, 35 over 3, 5. Put into the objective function, that gives us 80 over 3. We want to be able to compare it. So that equals 26 and 2/3. 26 and 2/3. So you can see this one is even smaller. We don't finish yet. We've still got one more vertex to go. So last one, vertex D. That's the intersection of the lines x equals 13 and y equals 5. So that's just a point 13, 5. We put 13 and 5 into the objective function. 13 plus 3 times 5, we get 28. So out of all of these, the one that gives us the lowest value is vertex C with these points here. So we can write our final answer as the optimal point is that coordinate 35 over 3, 5, and the minimum cost, or when we've minimized it, it minimizes to 26 and 2/3. So we'll just call that the minimized value. Example 10, a feasible region is defined by the following constraints. Find the optimal point and the optimal value given by these two different objectives. So we are going to draw all of this now. So these are the lines which I got from these points here. So the next thing I'm going to do is to shade the correct sides so I can see where the feasible region is. So my shading is done, and here I can see my feasible region there, which I'm going to label as R. Now, for me to use the vertex testing method to either maximize x plus y or minimize 3x plus 4y, what I'm going to need to do is to find out what the vertices of this polygon are. So to help with that, I'm going to label each vertex with a letter A, B, C, D, E. So there's 5 of them to do. So let's do that now. Right, so we've got all of the vertices worked out here. I've written down first of all for each vertex the two lines that intersect. After that, I've used my calculator to work out the coordinates of the point of intersection, and then I've taken the point of intersection and I've substituted it into the objective function. So I've done A and B for each vertex. Right, so if we start with part A, what we want to do is find the maximum value for x plus y. So we'll look through all of the coordinates here, and I can see the maximum one is this 10 and 3/35, which is vertex E. So then the optimal point is that 209/35, 144/35, and then the optimal value is 10 and 3/35. So that is maximizing x plus y. Then we'll go on to part B. So part B, which is what we want to minimize 3x plus 4y. So we can look for the minimum value of 3x plus 4y, and that's this, the 21 1/7. So that's vertex C on my diagram. So I'll just put C. So the optimal point will be 36/7, 10/7, and the optimal minimized value will be this 21 1/7. So 21 1/7. So you should now be able to do exercise 6C on pages 158 to 162.